Hello students, welcome back to MathWiz Java programming tutorials. In this video, I'll discuss some programs using method calling and let you know how to use return statement. Let's see the contents: introduction, special two-digit numbers in range, Armstrong numbers in range, LCM and reduce to lower fraction methods, dry run of prime number program. The prime number program I have discussed already in lesson number 33. The link is given in the description box, but over here only dry run. Now let's start. Main method in Java is a public static void method, and we write the program in main method only, starting of the program as well as ending of the program in main method only. But depending on the requirement, we create different methods and call in main method. Let's see the special two-digit numbers in range. What is the problem statement? Write a program to read a two-digit number only, 10 to 99. Add the sum of its digits to the products of its digits. Sum of digits plus product of digits is equivalent to the input number, then only return true, otherwise return false. Now consider the number 59. Sum of digits 5 plus 9, that is equal to 14. Product of its digits 5 into 9, that is equal to 45. Now sum of digits plus product of digits, that is equal to 14 plus 45 is equal to 59. That is equivalent to the original number. Now read a range in main method and call the special digit method. Range, maybe 10 to 99. Now let's understand dry run. Since there are only two digits, no need of a loop to extract digits. See the left side. 59 is divided by 10. 10 fives are 50 and 9 is the remainder. So quotient we get divided by sign and modulo sign results in remainder. Now see the program Boolean is special. Returns true or false. It's not void. Receiving one parameter, that is int n, and int first is equal to n divided by 10, that is 5. Int last is equal to n modulo 10, that is 9. First plus last stored in sum. First multiplied by last stored in product. Now sum plus product, if it is equal to n, the original number, yes, true, return true, otherwise return false. See, if and else, both of them have return statements, then the compiler accepts. Let's see a Java program. In the Java environment, we see the same program. Contents of special class. Let's understand main method. Program to display special two-digit numbers and enter a range between 10 and 99. That means if the user gives 10 as well as 99, 99 minus 10, that is equal to 89, plus 10 included 90 times that for loop will work. Now before for loop, we have couple of statements. Int a is equal to sc dot next int. B is equal to again sc dot next int, reading a range. Now there are three conditions. A should not be less than 10. So if A less than 10, it is not a two-digit number. B greater than 99, then also it is not a two-digit number. B cannot be less than A because we are running the loop in plus plus in forward direction. So if at all, if A less than 10 or B greater than 99 or B less than A, invalid input system.exit 0. You can give proper message also here. If this condition is not true, then for loop we are starting taking the range. j is equal to a, j less than equal to b. If user gives, let's suppose 10 to 50, those many times it works, 10, 11, 12, 13, 14, and so on and so forth. Every time it is calling is special method, which is a Boolean method. Is special parenthesis j. Now, if is written in such a way, any expression you give should return either true or false. We know so far relational operators return true or false. So we've used so many of them. Now we are using a method. How do we know it is a method? Some characters or a word followed by parenthesis is a method. So is special j. J is initially 10. J will be sent to n, call by value. And the program which I have discussed already returns true or false. 10 is not a special, two-digit number. 10 is not a two-digit special number. So, this method is special returns false. If false, there is no else part, so nothing will be done. Then 11, 12, 13, 14, 19 is a special two-digit number. So, is special returns true. True what? J is a special number. So, J will be printed. Let's see the execution of the program. Compile. Then main. Okay. Let's give 10 and 50. 19, 29, 39, 49. This is the output. Let us see Armstrong numbers in a range program. Problem statement is write a program to check whether a given number is an Armstrong number or not. What is an Armstrong number? Let's suppose 153. 1 cube plus 5 cube plus 3 cube should be equivalent to 153. 1 cube is 1, 5 cube is 125, and 3 cube is 27, which is equivalent to 153. It is equivalent to original number. So, our method should return true if this condition is true. Now read a range from the user and print all the Armstrong numbers in the range. So we take a main method, we try to read and call Armstrong number. Now, Boolean is Armstrong, extracting digits, and then sum is equal to sum plus d cube. Let's see the dry run. Extracting digits program I have explained in lesson number 22. Link is given in the description box. Now, num is equal to n. We have preserved num 153 because in the while loop n becomes 0, then only it comes out. Now, n is initially 153. N greater than 0. Yes, 153 greater than 0. True. D is equal to n modulo 10. 153 modulo 10. 10 15s are 150. 3 is the remainder. Now, sum equals to 0. 0 plus 3 cube. That is equal to 27. Now, the next statement, n is equal to n divided by 10. 153 divided by 10, we want quotient, that is 15. And we are storing in n. So, in the next iteration, n becomes 15. Is 15 greater than 0? True. 15 modulo 10, that is 5. 5 cube should be added to the previous sum, that is 27. 152 is the sum. N is equal to n divided by 10. 15 divided by 10. 10 ones are 10. So 1 is the quotient stored in n. Third iteration. Is 1 greater than 0? True. 1 modulo 10 is 1 only. 152 plus 1 cube is 153. Now n is equal to n divided by 10. 1 should be divided by 10. 10 zeros are 0. 1 is the remainder, but quotient is 0. That means n is 0. The condition is n greater than 0, which is false, comes out of the program. By that time, sum is 153 and the num which we have stored before while loop is 153. And if num is equal to sum, return true, otherwise return false. This is the concept of Armstrong number which returns true or false. Let's see a Java program here. Class Armstrong. Is Armstrong, we have already decided this is the content. Now main method. New scanner program to display Armstrong numbers. Enter a range. A and B are read. Let's say 100 to 1000. Starting a loop. J is equal to A, J less than equal to B, J plus plus. If is Armstrong J, the method is called. If it returns true, then only J would be printed. Let's execute the program and see. Main, C is Armstrong also static method. So we've called directly. Enter a range, let's say 100 to 1000. In that, only 4 Armstrong numbers are there: 153, 370, 371, 407. And very few Armstrong numbers are there. Now, LCM and reduce to a lower fraction methods. Now write a program which has two methods. First one to find LCM of given two numbers, and second one is to reduce to a lower fraction of the given two numbers. For example, LCM receives two parameters, int A and B, reduce int A and B, and we call the methods in main method. But we need to understand a little bit more about it. LCM can be found using two methods in maths. First one is long division method. Second one is product of numbers upon HCF. In these two ways, finding LCM would be easier if we find product of numbers upon HCF. So we've decided that HCF should be there for LCM. Now reduce to a lower fraction. Numerator and denominator we read. This also requires HCF. How? Numerator is, let's assume, 1000. Denominator 3000. HCF, that is highest common factor of both the numbers, is 1000. Now numerator upon HCF, that is 1000 upon 1000, is equivalent to 1. And denominator upon HCF, that is 3000 upon 1000, is 3. That is, the fraction is 1 upon 3 reduced. So in both the methods, reduce as well as LCM, we require HCF. So as a programmer, we write a private method which is not visible to the user, that is HCF. So in this program, main method, HCF method, LCM method, reduce method should be there. Let's see the program in Java environment. Let's see the contents of LCM underscore reduce. Here, main method in which we have declared two integer variables, w is equal to 6 and x is equal to 8. And we are calling LCM with these two parameters. And wx can be taken input from user also. But we are concentrating on methods and method calling. LCM is a static method, so directly calling. You know that otherwise we need an object. If had it been, it is an instance method. Now Wx parameters are copied onto A, B, pass by value. Now we are further calling HCF method by sending A, B, that is 6 and 8. HCF is a method which is returning an integer. So after calling HCF, we'll store in a variable called HCF, whatever is sent by HCF method. Here, uppercase HCF is the method name, lowercase HCF is the variable. Fine. Now control will go from here to HCF, and then it returns some highest common factor. What does it return if we send 6 and 8? It returns 2, highest common factor. Now we are saying LCM of A and B, that is 6 and 8, is A multiplied by B. 6 8s are 48, divided by 2 is 24. That is LCM of 6 and 8. Now we are sending 1000 and 3000 to the method reduce. Y and Z are the parameters. It's a static method. Y and Z are copied onto AB. Again calling HCF here with AB, that is 1000 and 3000, which returns 1000 to HCF variable. Now reduced fraction is A upon HCF. A is what? 1000. 1000 upon 1000 is 1 slash 3000 upon 1000 is 3. That is 1 upon 3 would be displayed. Now, the HCF method I have already discussed in lesson number 20, but now we understand in terms of returning. So, int HCF is a method which should return integer. Initially, h is equal to 0, highest common factor, we are storing 0. But we are finding minimum out of 2. What is 6 and 8? Let's assume minimum is 6. So our loop starts from 6. J is equal to min. J greater than equals to 1. J minus minus. Starting from 6 and going in reverse direction. 6, 5, 4, 3, 2, 1. Now, every time we are checking if A modulo J double equals to 0 and B modulo J double equals to 0. Is 6 divisible by 6? Yes. Is 8 divisible by 6? No. So, minus minus, nothing will happen here, because if this condition is true, then only these two statements. Otherwise, no. So, then 5. 6 is not divisible by 5. And operator intelligent. If 1 is false, it won't check the next one. Then 4. 6 is not divisible by 4. 3. 6 is divisible by 3. Then it checks. Is 8 divisible by 3? No. So again minus minus 2. Is 6 divisible by 2? Yes. Is 8 divisible by 2? Yes. So H is equal to J. Look at this. We cannot say return J here. We cannot say return J here. Why? Because only if is there for us. As a programmer, we know even if we send prime numbers, common factor would be 1. But the compiler doesn't know. If I execute this control K, it gives me an error saying that what? Missing return statement. Because only if it is true return J we are saying. So it won't allow us. There should be either else or at the end we need to give some return statement. In that case, why we are sending here return J? Why? Because H is equal to J, first of all, we say that is highest common factor would be 2. And then we can say break the loop, come out of the loop, and then return the H. 2 will be returned. Anyway, I have to write a return statement at the end. Or we can do like this also. Return J here, J is 2, and store, because if we don't store, H will be 0. That is not a good programming practice. So first of all, update H variable with 2, that is J, and then return from 2 places. So instead of returning 2 places, we write the program in such a way, H is A, break the loop, and then return the H. This is the program. Let's execute and see. There are so many methods. We may make them private, or from some other class in the same package they can be used. So I am leaving them as package level main. Okay. And then LCM of 6 and 8 is 24. Reduced fraction is 1 upon 3. In the main method, we can have a menu. Depending on the choice, we can call all of them. We know the menu programs. But here, we are just trying to understand the return statement. That's why I just have written LCM and reduce like this. Now, let's see dry run of prime number program with 3 different inputs. If you see left side, that boolean is prime int n accepting a number. If n is 1, it's not a prime number, neither prime nor composite. Return false because it is not prime. In the for loop, we try to check if any extra factor is there, that is composite number or not. If composite, return false because it is not a prime. If n is not 1, n is not 1 and not a composite number, then only the control reaches to the last return true statement. That means number is prime. So first dry run, right side, n1 input. If n is 1 true, then return false because it is not a prime number. Second case, n is 15, which is a composite number, but the program has to decide n is 1, false, so no problems, control reaches to for loop. Now, for loop starts at 2, CTR is 2, CTR less than equal to n by 2. Now, what is n 15? 15 by 2 is 7. It takes only quotient. So, this for loop is supposed to work from 2 to 7. First time CTR is 2. Is 2 less than equal to 7 true? Then see the next column in the dry run. N modulo CTR double equals to 0. Excuse me. That means N is 15. CTR is 2. 15 modulo 2. 2 sevens are 14 and the remainder is 1. So it is not 0, false. Then CTR plus plus. 3 is 3 less than equivalent to 7? True. Now, n modulo CTR, n is 15 only, but CTR changed to 3. 15 modulo 3. 3 5s are 15 and the remainder is 0. True. That means we need to return false. Why? Because our for loop is starting from 2 and ending at n by 2. That means neither 1 nor n we have considered in the for loop. Apart from 1 and n, if we get one more factor, that means it is a composite number and the method returns false because composite number. So 15 understood. Now the third case. N is 11. It's a prime number, we know that. Now, n is 1 false. CTR 2, 3, 4, 5, sixth time it is false. Why? Because CTR less than equal to n by 2. Now n is 11. 11 by 2 is 2. 5s are 10. So our loop works 2, 3, 4, 5 times, sixth time false. Okay. Now see the column n modulo CTR double equals to 0. Is 11 modulo 2 0? No. 2 5s are 10. Remainder is 1. It is not equal to 0. Then our CTR plus plus 3. 11 modulo 3. 3 3s are 9. Remainder is 2, not 0. False. 11 modulo 4. 4 2s are 8. Remainder is 3, not equal to 0. False. 11 modulo 5. 5 2s are 10. 1 is the remainder, not 0. But CTR becomes 6 and our loop control becomes false. When for loop is executed, the entire all iterations, and then comes to the next statement that is return true. That means 11 is a prime number. Now let's see practice exercise. Read a range from user and display all the palindrome numbers in the range. Palindrome, I have explained you in while loop. So please see that video. Read a range in main and then call palindrome, which returns true or false. Similarly, second one, read a range from user, display all the perfect numbers in the range. Third one, sum is equal to 1 plus 2, 1 by 1 multiplied by 2. In the first subterm, sum is happening divided by factorial. Again, plus sum of 1, 2, 3 divided by factorial till 3, and so on and so forth. The above program requires three methods, one for addition, second for factorial, and then main method, which calls both the methods and displays the sum. This practice exercise I have given in the description box. Refer chapter 3 of Essentials of Computer Applications for further understanding and practice exercises. The next video is about some programs on method and constructor calling. Thank you.